Welcome, and thank you for joining today's session. We'll be exploring the IDIMM solution, a breakthrough approach for testing next-generation memory technologies. We will walk through the evolution of DDR testing, the challenges we face with DDR5 and MRDIMM architectures, and how the instrumented DIMM, or IDIMM, provides a powerful new path forward. Let's begin with a bit of history. In the early days of DDR memory, testing was relatively straightforward. With DDR1, thin small outline packages known as TSOP made it possible to directly probe the pins of the DRAM component itself. Probing could also be done on plated through-hole connectors, giving engineers direct electrical access to signals they wanted to observe. As time went on, however, things began to change. Different forms of ball grid array or BGA packaging and surface mount or SMT connectors entered the picture. While BGAs and SMTs offered manufacturing and performance advantages, they also created new challenges for signal probing. Various package and slot interposers were developed to support signal integrity measurements and protocol testing, but DDR architecture did not stand still. Each new generation of DDR memory increased speed and complexity. Probing became harder, packages grew denser, and system channels became highly tuned with razor-thin margins. At the same time, platform integration meant fewer opportunities to tap into signals for testing, and the test equipment itself often lagged behind, struggling to keep up with increases in data transfer rates. This history brings us to where we are today, facing the challenges of DDR5. DDR5 represents a major leap forward in memory technology, but it also introduces significant hurdles for validation and debugging. Traditional mid-bus passive probing with slot interposers is still widely used and well understood. However, at the high transfer rates we are dealing with right now, these approaches begin to show their limits. Instead of providing clear, quantitative insights into signal integrity, the measurements often become more qualitative in nature. Protocol analysis is still possible, but only if the logic analyzer can support the signaling rates and if the channel can continue operating despite the added interconnect length introduced by the probe. The reality is that DDR5 DCA transfer rates, especially in server-class modules, already exceed what current logic analyzers can handle. For example, the host channel DCA signal transfer rate on the current generation of DDR5 RD modules is 6.4 gigatransfer per second or higher, which corresponds to a DCA signal frequency of 3.2 GHz or higher. Meanwhile, the maximum signal frequency supported by today's top-of-the-line logic analyzers is only 2.5 GHz, meaning our conventional toolsets are no longer sufficient. So, how do we overcome this challenge? The answer begins with innovation in interposer design. To extend testability into DDR5, we look to the active slot interposer. Unlike passive designs, the active interposer integrates a DDR5 RCD, a register clock driver, operating in what's called validation pass-through mode. The DDR5 RCD component forwards chip select and command address signals to the logic analyzer, while also expanding 7-bit wide dual data rate or DDR host command address bus into 14-bit wide single data rate or SDR DRAM command address bus. This is essential to our ability to capture bus protocol because it makes the signals analyzable by existing test equipment without requiring that the tools themselves leap ahead to the next technology node. Using the previously mentioned example, if a 6.4 gigatransfer per second, the RDIMM, is tested, the command address signals forwarded by the interposer-based RCD to the logic analyzer run at 3.2 gigatransfer per second, or 1.6 gigahertz, which is supported by the logic analyzer. The RCD and the interposer also provides equalization functions like decision feedback equalization and continuous time linear equalization. These techniques improve or open the signal eye, which enables us to capture signals with more precision and at higher transfer rate. Importantly, the data bus signals are not altered. They pass through the interposer with minimal impact. Let's dive deeper into how these active interposers evolved. The first generation RDIMM interposer, called FS2670A, was designed to work with RCD02 through RCD04 components. For this setup to work, the system must train the interposer-based RCD before testing can begin. In practice, this setup successfully booted and captured traffic at 6.4 gigatransfer per second. Work is ongoing to optimize its performance at 7.2 gigatransfer per second. Building on this, the follow-up interposer FS2675A was created to support the next generation of RCDs, specifically RCD05 and RCD06. The design target is even more ambitious, supporting DDR5 data rates up to 8.0 gigatransfers per second with RCD05 and up to 9.2 gigatransfers per second with RCD06. This support requires additional design improvements, particularly to ensure robust signal integrity at those higher speeds. These developments mark significant progress, but the real challenge appears when we move from RDIMM to MRDIMM. Multiplexed rank DIMMs, or MRDIMMs, represent a major step forward in DDR5 server memory. But with innovation comes complexity. An MRDIMM can contain 40 or more DRAM devices organized into multiple ranks or pseudo-channels. It also introduces new buffer components, the MDBs, multiplexed rank data buffers, and the MRCDs, multiplexed rank clock drivers. The MRDIMM implements a multiplexing function between the two DRAM side data buses, combining them into a single host side data bus that runs twice as fast. This creates a highly tuned system optimized for single DIMM per channel configurations that provides high memory capacity with high channel bandwidth. While this architecture enables high performance, it also complicates testing and validation, as we will see on one of the next pages. MRDIMM implements an 80-bit dual data rate data channel, which is divided into two independent 40-bit or 5-byte subchannels. Each data byte in the subchannels on the host side is connected to a dedicated MDB component, resulting in a total of 10 MDB components per MRDIMM, 5 per subchannel. The current generation of MRDIMM is designed to support a 12.8 gigatransfers per second host data channel rate. On the DRAM or local side, each MDB component creates two copies of the data signals, one for each pseudo-channel or rank. Each of these two local copies operates at 6.4 gigatransfer per second, which is half of the speed of the host channel. An MRDIMM contains a single MRCD component that receives a 14-bit wide dual data rate DCA bus, 7 bits per subchannel, running at the same speed as the data channel, which is 12.8 gigatransfer per second. The MRCD component on MRDIMM performs the same functions as an RDIMM, decoding DCA signals and expanding the 7-bit dual data rate host side DCA bus into a 14-bit single data rate local CA bus. Since the data bus on the local or DRAM side operates at half the channel speed, the resulting transfer rate of the local command address bus is 1/4 of the host channel DCA bus, or 3.2 gigatransfers per second. Testing MRDIMM protocols in the traditional way is extremely challenging for several reasons. MRDIMMs are optimized for very high speed operation with physical module implementations that are not conducive to modifications. Probing based on the passive interposer approach would alter the environment beyond the assumptions used to architect the overall system channel. In addition, the operating frequencies measured with this approach exceed the limits of available test equipment. The pass-through mode required for active probing is not available on the MRCDO2 under normal operation. This means that we cannot tap into command and address lines as we could with RDIMM active interposers. To address these issues, we are creating an instrumented DIMM, or IDIMM, rather than relying on external interposers or struggling with passive probing. The IDIMM integrates the necessary test interfaces directly into the MRDIMM itself. It provides a connection for a logic analyzer, enabling direct protocol visibility without disrupting the high-speed system channel. In other words, the IDIMM is designed from the ground up to meet the testing challenges of DDR5 MRDIMMs. The first implementation of IDIMM is based on a industry standard MRDIMM row card D1. To support additional connectivity, the standard MRDIMM is extended to accommodate the cable interface and supporting components. Despite these modifications, the original MRDIMM electrical targets are preserved. The high-speed layers remain intact, ensuring system behavior matches that of a production MRDIMM. The IDIMM enables analysis of all 4 pseudo-channel command address signal copies, as well as BCOM buses, which control MDB components for each of the subchannels, which further broadens its utility for system-level debug. From the perspective of the host system, the IDIMM initialization, training, and operation will look and feel essentially the same as with a standard MRDIMM. This transparency is important as it allows testing in realistic operating conditions. Finally, let's look at the concept in a little bit more detail. The IDIMM module measures 133.35 mm by 50 mm and is fully compatible with the industry standard DDR5 MRDIMM connector. Its extended port houses headers for the logic analyzer cable interface and the secondary sideband bus direct connector, along with supporting components such as clock dividers and power circuits. Coaxial cables are pre-assembled, enabling direct connection to Keysight U4164A logic analyzer modules. Together, these design choices allow the IDIMM to deliver visibility, control, and complete insight into the MRDIMM bus protocol. In summary, memory testing has evolved dramatically from simple probing in the DDR1 era to the complex challenges of DDR5 MRDIMM. Traditional methods can no longer keep up, but with the instrumented DIMM or IDIMM, we have a powerful new tool that integrates test access into the module itself. This solution enables accurate, high-speed protocol analysis without compromising system performance. It represents a major step forward for engineers working to validate and optimize the most advanced server memory technologies. Thank you for your attention.